Hello everyone, my name is Fang. I just got my PhD in the Institute of Theoretical Physics, the University of Chinese Academy of Sciences. I will be a postdoc in the Kavli Institute for Astronomy and Astrophysics in the Peking University. I will introduce to you my recent work on probing the spin of the supermassive black hole by detecting the gravitational waves of a nearby black hole binary, cooperated with the Qing-Guo, Huang, and Xian. The origin of the black hole binary detected by the LIGO and Virgo is still unknown. They are traditionally thought to be formed as the isolated field binaries, or they could form dynamically in the globular cluster. According to the recent studies, the galactic nucleus is also an important place for the binary black hole to form. The module rate of the binary black holes is enhanced in the nuclear star clusters, which is comparable to the LIGO-Virgo event rates due to the following reasons. They could be tightly perturbated by the supermassive black holes and enhance the module rates through a mechanism called the Kozai-Lidov effect. The escape velocity for the compact objects near the supermassive black holes is high. There is a mass segregation process increases the density of the black holes around the supermassive black holes. Supermassive black holes can tightly capture the binary black holes to its ground orbits. And if the environment is gas-rich in an active galactic nuclei, binary black holes can grow and merge more efficiently. The observations indicates that the supermassive black holes are universally spinning, especially the results from the X-ray reflection spectroscopy indicates that most of the supermassive black holes have large spins. So we started this triple system composed of a black hole binary of standard mass and a spinning supermassive black hole. The binary black hole revolving around each other in the inner orbits, while the central of mass revolving around the supermassive black hole at a larger outer orbit. The inner binary is perturbated by the supermassive black hole, while the Newtonian quadruple perturbation will cause the binary black hole to move and cause a Lidov oscillation. The conservation of the total orbital angular momentum at the Newtonian quadruple order will lead to the exchange between the inner orbital eccentricity and the inclination angle between the two orbits. Analogous to the Newtonian gravitational force from the electric parts of the gravitational field, and the mass of the triple system is dominated by the mass of the supermassive black hole. The angular momentum of this triple system is dominated by the spin of the supermassive black hole, which will induce a strong gravito-magnetic field in the space-time. Then the binary black hole as point particle will move, and this gravito-magnetic field will be affected by this gravito-magnetic force, decomposing these accelerations into the inner and outer orbital motion, and use the method of oscillating orbital elements. We could get the circular evolution of the spin effect after the double average of the two orbits. The first equation describes the streaming polarization of the outer orbits, while the omega-3 angle is the longitude of ascending node of the outer orbits. The rest three equations describe the appreciation of the inner orbits due to spin effects. In this case, the total orbital angular momentum will approximately the outer orbital angular momentum is not conserved anymore. Thus, we need a generalized Kozai-Lidov formula, which could include the involving of the outer orbital plane. We derived the generalized Kozai-Lidov formula in this work, where the secular dynamics will have a dependence on the relative angle, longitude of ascending nodes of the two orbits and the angle between the outer orbital angular momentum and the spin direction. The generalized Kozai-Lidov formula will degenerate to the standard Kozai-Lidov formula in the case when the outer orbital plane is approximately constant and the outer orbital angular momentum is set along the axis in this limit. The variation of the outer orbital plane will cause the three-body 1pn effect to begin coupled in, which is dominated by the theta polarization to begin coupled in the secular dynamics. Since the theta polarization typically places the longitude of ascending nodes. In this general reference frame, the theta polarization include both the polarization of the inner orbital angular momentum and the inner orbital range length vector around the outer orbital angular momentum, were described by these three equations. Due to the large mass of the supermassive black hole, the theta polarization, the amplitude of the theta polarization could reach to or even larger than the inner binary 1pn polarization. There is a typical modulation on the Kozai-Lidov oscillation due to spin effects. The maximum eccentricity excited by the Kozai-Lidov oscillation in our triple system is related to the conserved quantity in the Newtonian classical order by this equation, where spin will cause this conserved quantity to evolve this way. Where these three vectors represent the spin direction and the direction of the inner and outer orbital angular momentum, respectively. Next, we will move to the numerical results of the spin effect on the gravitational waves of the binary black hole. In this example, we have this initial conditions. While the signal mass are while the signal black hole are of mass 10 and 20 solar mass, the third body is a supermassive black hole, the same in our galaxy center. This picture shows the evolution of the peak frequency of the gravitational wave emitted by the binary black hole. The peak frequency corresponds to the frequency of the gravitational wave at the maximum values of the radiation power, which is closely related to the eccentricity. In this case, the peak frequency of the gravitational wave locates in these bands in the lifetime evolution of the black hole battery. We compared the difference of the waveform parameters within the first 12 evolutions first 12 years of evolution. In this figure, we could see that the period of oscillation, of Kozai-Lidov oscillation is shifted, and the inclination angle measured by an observer, which is assumed in the x direction, will evolve very differently. And we compared the fitting factor of the two waveforms by the detection of Lisa. The waveform depends on the inclination and the assumed angle measured by the observer. The waveform calculated from the model without the spin effect is labeled with H1, and that from the results with spin effect as H2. The fitting factor defined this way describes the difference between these two waveforms. For 4 years detection by Lisa, the result of the fitting factor is 0.834. When assuming the source in our galactic center, this fitting factor is smaller than the threshold value, and the SNR is not. That indicates that the signal is distinguishable from that without spin. In the second example, we study the unique characteristics on the gravitational waves of the barrier black hole resulted from spin. The maximum eccentricity excited by the Kozai-Lidov oscillation is through these two equations as stated before. The variation of the we evolve this triple system up to 1.5 post-Newtonian order, in which we have included the three-body 1pn effects. The red line is the result when spin is 0.9, and the black dashed line is spin 0. In this example, the variation of the eccentricity of the maximum eccentricity in the neighboring Kozai-Lidov circles will cause the corresponding peak frequency to be different by 1 millihertz among its maximal values. So we compared the signal to noise ratio for the first two peaks, which is separated by 4 years in two cases when the supermassive black hole spin is 0.9 and 0.0. The only varying parameter in the waveform is the eccentricity. So the result is that when spin is 0.9, the SNR for the first two peaks are respectively 260 and 283, while the SNR for the spin 0 are both 260. So the difference of the SNR in the first two peaks due to the variation of the maximum eccentricity is 23, which is detectable by Lisa, especially when it is extended to 10 years. As a conclusion, our above results imply that the spin of the supermassive black hole could leave a distinguishable imprint on the waveforms of the binary black hole by Lisa's detection, which could potentially be used to prove the spin of the supermassive black holes. That's all. Thanks for your listening. If you have any questions, please let me know.